Welcome to Kognito Key. Today, we're diving right into a highly focused explainer designed to completely demystify series magnetic circuits. If you've ever stared down a really complex magnetic system and just wondered, where does the math even begin here? Well, you're in the right place. Let's just jump right in.
Let's kick things off with a massive, highly practical question that electrical engineers face literally all the time. How do we actually measure the magnetic force flowing through a complex, multi-material system? Think about the real-world applications we rely on every day, like electric motors, transformers, or massive generators. They aren't just carved out of one simple block of iron, right? They're built from varying dimensions, totally different shapes, and multiple materials, all working together in one system.
Okay, let's dive into this. By definition, a series magnetic circuit is a circuit that has a number of parts of different dimensions and materials, but here is the absolute most important part. They carry the exact same magnetic field. It's kind of like water flowing through different sized pipes that are all connected in a single line. No matter the pipe's width, the total water current flowing through stays constant. In our magnetic circuit, that magnetic flux remains perfectly constant across all the different sections. So when you're analyzing a typical circuit, like say a solenoid wound around a multi-part core, you're going to encounter a few key variables. First, we've got the cross-sectional areas and the lengths of the different sections. Then we have the relative permeabilities of the specific materials. That's basically just a measure of how easily they allow magnetic fields to pass through them. And quite often in real-world engineering, we also have to account for an air gap, which introduces its own specific area and length right into the series. Section 1. The math. Calculating total MMF. Let's break down how we actually crunch these numbers. All right, here is your 5-step procedure for getting this done. Step 1 is simple preparation. Just divide the magnetic circuit into its different sections based on the material and size. Step 2, determine the flux density, or B, for each section. You do that by dividing the flux by the area. Step 3 is finding your magnetizing force, H. Step 4, take that force, H, and multiply it by the length of that specific section. And finally, step 5 is the absolute easiest part. You simply add all those values together to get your total MMF. Easy, right? Now, you might actually hit a bit of a roadblock at step 3 if an exam problem or a real-world spec sheet doesn't give you the relative permeability, μr. So the crucial point is this. If μr is missing, do not panic. You can actually compute the value of the magnetizing force, H, directly from something called the BH curve. Which brings us to section 2, the material factor, understanding the BH curve. So the BH curve, which is commonly known as the magnetization curve, is simply the graph plotted between the flux density, B, and the magnetizing force, H, of any specific material. Think of it as a visual cheat sheet. It shows you exactly how a material behaves and reacts when you subject it to a magnetic field. Now, you might be wondering, why do we even need a specialized graph for this? Well, it's because materials fall into two very different behavioral categories. On one side, we have magnetic materials. Their magnetic response is totally nonlinear, which means their relative permeability actively shifts depending on the flux density. But on the flip side, we have non-magnetic materials and air gaps. For these guys, the permeability is just a constant absolute value, μ0, which is strictly 4 pi times 10 to the power of -7. And this brilliantly illustrates the core difference. For magnetic materials like cast iron or sheet steel, that curve shape is nonlinear because, like we said, their permeability actively shifts. But surprisingly, for non-magnetic materials like plastic, rubber, or an air gap, the relationship is perfectly constant and linear. They just don't adapt to the field. Understanding this fundamental material distinction is absolutely key to solving those complex circuit problems with total confidence. Mastering this math and understanding exactly how different materials interact with magnetic fields is foundational for electrical engineering. It is precisely how we design the powerful motors, generators, and transformers that run our entire modern world. Thank you so much for learning with us today. Please subscribe to Kognito Key for more structured engineering insights, and please like and share this video with your fellow learners. Keep calculating, and let me leave you with this. When you look at the electric vehicles and massive power grids shaping our future, what complex magnetic system will you decode first?